Welcome all my dear student. Welcome all my dear student of SYBSc physics class. Okay, in previous lecture we have studied last one, distortion, that is defect in image belongs to monochromatic aberration. Now in this lecture we are going to see the chromatic aberration. Chromatic, chrom means color. Now obviously chromatic aberration means there is a defect in image due to colors. Okay, so if the light rays coming from the object, suppose this is the object, and white light rays are coming from the object and falling on this lens, which are not monochromatic. They are having different colors. They are having different reflective indices. Hence, focal length of lens are different for different colors. That is, focal length of lens different for different wavelength and for different refractive indices. I am again going to tell you that if the light coming from the object and falling on the lens are not monochromatic, refractive index not monochromatic, that means what? Refractive index, and hence the focal length are different for different wavelengths of the light. And thus, make your concentration here. The rays of white light, for example, mercury vapor lamp, rays of mercury vapor lamp. The rays of white light after refraction through the lens form number of colored images of different size at different positions, and this defect is known as chromatic aberration. This is very important and interesting one. So I am again going to repeat this one. What is chromatic aberration? The rays of white light after a refraction through a lens form a number of colored images of different size at different positions, and this defect is known as chromatic aberration. There are two types of chromatic aberrations: axial or longitudinal chromatic aberration, and second one is lateral or transverse chromatic aberration. First of all, we are going to see axial chromatic aberration. See here, this figure illustrates axial chromatic aberration. See here how it takes place. When a beam of white light is incident on the lens, it get dispersed into constituent 7 color. What I say, when beam of white light is incident on a lens and it get dispersed into its 7 constituent colors or 7 constituent colors. The deviation produced by the lens is different for different colors, and dispersed rays come to focus at different position or at different point on the axis of lens or on the principal axis. Refractive index of material, it always remember that refractive index of the material decreases with increasing focal length. Refractive index mu r is for red color. It is less as compared to refractive index of yellow color, and refractive index of yellow color is less than refractive index of violet color. This is the extreme color. This is the extreme color. This is intermediate color. Red, yellow and violet. First one is red color and middle color is yellow and last color is violet. So refractive index of red color is always less than the refractive index of yellow color, and refractive index of yellow color is always less than refractive index of violet color. But wavelength of red color is always greater than wavelength of yellow color, and wavelength of yellow color is always greater than wavelength of violet color. This is the controversy, and therefore it is found that the violet rays produce larger deviation, violet rays produce larger deviation as compared to deviation produced by red colors, and this is illustrated in this figure. Therefore, from the equation 1 upon F is equal to mu minus 1 in bracket 1 upon R1 minus 1 upon R2. This is the lens maker's equation. According to this relation, the focal length of lens is smaller. Focal length of lens is smaller for violet rays. Focal length FV is smaller for violet rays. That is, focal length of violet rays is less than focal length of red rays. Sorry, this is okay. According to this relation, the focal length of a lens is smaller for violet color and larger for red color. Or we can say that according to this relation, the focal length of a lens is smaller for violet color than red color, or violet rays than red rays. Therefore, violet rays are brought to focus near the lens, whereas the red rays are focused away from the lens. And the image due to various other colors are lying in between these two extreme color, violet and red color. Okay. Thus, lens produces number of colored images of a white object, resulting in a linear spectrum. And therefore, make your concentration here. This is very important definition regarding to axial chromatic aberration. The defect, this is happen along the axis and is axial chromatic aberration. The defect which results in blurring the image due to lens along the axis is called axial or longitudinal chromatic aberration. If FV and FR, the focal lengths corresponding to violet and red rays respectively, then the difference between these two, wavelength of violet to red, is taken as a measure of the longitudinal chromatic aberration. Larger is the difference, that is, larger is the axial chromatic aberration. Minimum is the difference between these two focal lengths, then longitudinal chromatic aberration will be minimum. Okay. Now, the focal length F of this thin lens related to refractive index of material of the lens is given by this equation, obviously. Okay. Now, when we differentiate, suppose this is equation 1. When we differentiate this equation 1, we will have minus differentiation of 1 upon F is minus dF upon F square. And differentiation of this term is mu minus 1 is d mu. Okay. And radius of the lens are always constant. So, there is no differentiation. Why there is no differentiation? Because even though this phenomenon is happen during whole phenomenon, the radius of the curvature of the lens remains constant. Okay. Therefore, but from this equation we can write here simply from this relation we can write, see here, 1 upon r 1 minus 1 upon r2. That means this term is equal to 1 upon f into mu minus 1. We simply brought this term towards this side and we will get it. Suppose this is relation number 2. Okay. Now, when we substitute the value of this term, that is 1 upon f is equal to, 1 upon f into mu minus 1 in this equation, we have minus df upon f square is equal to d mu upon f into mu minus 1. This one f is getting cancelled with this f and we will have only minus df upon f is equal to d mu minus what? Mu minus 1. Okay. Suppose this is equation 3. Okay. This quantity d upon mu minus 1 is called dispersive power and it is always denoted by omega. Therefore, omega is equal to d mu upon mu minus 1. Suppose this is equation 4. Okay. But here, see here, d mu upon mu minus 1 is equal to minus df upon f, and here d minus mu upon mu minus 1 is equal to omega. Hence we can equate this equation 2, equation 3 and 2. After equating these two equations, we will have minus df upon f is equal to omega, or simply my df is equal to minus f into omega. What is df? df is the difference between these two focal length. Okay. Or instead of this we can write simply here df is equal to minus omega into f. Okay. What is df? df is the difference between two focal length corresponding to extreme color. And from this equation, it is clear that longitudinal chromatic, this is the longitudinal chromatic aberration, because this gives the difference between two focal length of extreme color, violet and red. So longitudinal chromatic aberration is equal to dispersive power into mean focal length. Okay. Now, lastly, we are going to see the second type of chromatic aberration, that is transverse or lateral chromatic aberration. And in lateral chromatic aberration, just a minute, I want to clean the board. Sorry for distortion. There is somewhat disturbance due to some technical problems. So here we are going to see the last type, that is second type of chromatic aberration, that is lateral or transverse. Lateral or transverse chromatic aberration. As we know that the lens, when white light is incident on the lens, it will produce different images for different colors, and these images are at different position. Suppose see here, suppose this is the convex lens, and in this lens, suppose this is the object, and from this object two rays are coming. This is the first rays, this is the rays from white object, and this is the second ray, which are also incident on this side. Okay. Now, after refraction, these are the violet rays. These are the violet rays which refracted after refraction, and they come to focus and gives the image A prime, B prime. This is the image. Now, red rays, red rays. Red rays are come to focus and gives image here. This is A double prime, B double prime. That means this is the image that is due to red color, red image, and this image is due to violet color. So it is violet image. Okay. And this is the difference between. See here, this is the height for violet color, this is the height for red color. So HR minus HV gives the difference in height of images. See here, as we know that violet rays having larger deviation, so they forms the image near the lens, whereas red rays are having larger focal length because their wavelength is larger. So red rays form the image away from the lens. So this is the image which formed by red rays, and this is the image which is formed by the violet color. So this is violet image, and the difference in height is the major. This is the lateral or transverse. This is taken in this way. This is lateral or transverse chromatic aberration. Okay, there are n number of intermediate colors are lying in between these two. So this height is the measure, the difference in height, that is HR minus HV is the measure of lateral chromatic aberration. This means what? Higher is the difference in height, larger is the lateral chromatic aberration, whereas smaller is the difference between height of the image, then smaller is the lateral or chromatic aberration. In this way, we completed chromatic aberrations, that is lateral longitudinal or axial chromatic aberration, and second one lateral or transverse chromatic aberration. We shall stop here. Have a good day.